Hello everyone, welcome to my YouTube channel. So today I will discuss about the palladium catalyst CC and CN cross coupling reaction in the organometallic reaction. So first I will discuss about the discovery of the palladium catalyst cross coupling reaction. So carbon-carbon bond formation is one of the most important reaction in organic chemistry. So reaction involving the aryl coupling or alkyl coupling using traditional non-catalytic methods generally involve many steps. So although the copper-mediated aryl homocoupling using aryl iodide was produced by Ullmann in 1904, the majority of copper is in coupling reaction catalyzed by the palladium began in 1972 with the Heck reaction. So Heck reaction, which is the cross-coupling reaction of aryl halide and with an alkene, and the Kumata reaction, which is the cross-coupling reaction of an aryl halide and hydrogen. The most important contribution of all these cross-coupling reaction, however, came from the Suzuki. So he discovered the most useful and important transformation of the conversion of carbon-carbon bond in modern-day organic chemistry, the reaction known as the Suzuki-Maeda coupling reaction. Since this research by various groups over past 30 years, there leads to vast improvement of this reaction. So Sonagashira brought in the palladium catalyst aryl alkene coupling in 1975. Later, Buchwald in Hartwig introduced aryl CN and aryl CO coupling using palladium as a catalyst. In the meantime, a host other coupling reactions are also reported. Prominent among them are the Stille coupling, Yama coupling, legacy coupling reaction. So this is the carbon these cross coupling reaction are useful to form this carbon-carbon or carbon-nitrogen bond. So despite the traditional organic methods, that involve many various steps. So by using this cross coupling reaction, we can make the carbon-carbon bond or carbon-nitrogen bond in a single step. So here, this is some example where this is a Suzuki reaction where this aryl halide aryl halide is coupled with another. This is aryl coupling reaction. This is a aryl alkene coupling reaction, which is called the Heck reaction. This is the aryl and the alkene coupling reaction. This is called the Sonagashira reaction, and this is called the aryl and amine coupling reaction. This is a CN bond formation called the Buchwald-Hartwig reaction. So this is the classical example of the cross-coupling reaction by using the palladium as a catalyst. So over the years, Suzuki coupling has gained much more prominence than other coupling reaction. Many modifications have been introduced on the other original Suzuki and related reaction. For example, the use of the aryl chloride in place of iodide, bromides, introduction of electron-rich sterically bulky phosphine, carrying out the reaction at room temperature using palladium catalyst at the ppb level. This has certainly expanded the scope of palladium catalyst cross-coupling reaction. For this contribution in 2010, Nobel Prize for Chemistry was awarded to Suzuki, Heck and Legacy for their contribution in the palladium catalyst cross-coupling reaction. So among the other cross-coupling reactions, Suzuki cross-coupling reaction is very much important. So over the years, many modification was introduced to this Suzuki cross-coupling reaction. Aryl chloride is used in place of aryl iodide or bromide. Even the reaction is carried out in the room temperature, or the use of the palladium catalyst lowered down to the ppb levels. So contrary to the belief that this reaction is applicable only to the sp2 carbon substrate, post 2002 was witnessed the development of alkyl coupling of unactivated primary and secondary alkyl halide using 9 ppm derivative and nickel catalyzed instead of palladium. The functional group tolerance has been in the hallmark of the many palladium catalyst cross-coupling reaction. Efficient one-stage Suzuki annihilation of unprotected haloglycoside using water-soluble phosphine and palladium catalyst can also be achieved. Thus, the extending the reach of this reaction is biological chemistry as well. The Suzuki coupling has recently extended to the perforated aryl coupling reaction. So next I will discuss about the industrial application of the cross coupling reaction. So as the bi arrives at the common substrate with many natural products, the Suzuki coupling reaction has been used in the industrial preparation of many natural products and bioactive compounds. And the well-known anti-hypertensive drug valsartan is manufactured by Novartis, and the use of the Suzuki coupling has considerably reduced the number of steps and its synthesis. Another compound manufacturing the bulk quantity BASF using Suzuki coupling is a fungicide. So, using this cross coupling reaction, many bioactive molecules like the valsartan or the boscalid is synthesized by this Suzuki cross coupling reaction. And also the Hague reaction also used for industrial synthesis of common sunscreen agent 2-ethyl paramethoxycinnamate, herbicide, prosulfuron, and the singular or anti-asthma agent. And an important application in the Sonalosari coupling reaction is the enzyme synthesis of compounds that are using the anti-cancer therapy of the Bergman cyclization. So all this cross coupling reaction has a application in the industrial level. So next I will discuss about the cross coupling catalyst. So here mainly for the cross coupling reaction, the palladium is used maximum case. So though there are examples such as the nickel, rhodium, copper, platinum used in the cross coupling reaction. The palladium index is the most widely used metal for this reaction. So even palladium colloids and nanoparticle can be used and open the metal is associated with some ligands. Both palladium zero complex and the complex compounds are used. However, the active species is the palladium zero is all these cases. So palladium 2 presumably gets reduced to palladium zero by amide, phosphine, organometallic reagents such as the N-butyl lithium, trialkyl aluminium, or also by alkenes. So for all this reaction, palladium 0 precursor or palladium 2 precursor may be used, but for all this reaction, the active catalyst is the palladium 0. So when someone used the palladium 2 in this reaction, so this palladium 2 is reduced to palladium 0 in the reaction medium by using the amines, phosphine, or organometallic reagents such as N-butyl lithium or trialkyl aluminium, also even by the alkanes. So here how this palladium 2 is reduced to palladium 0. So first example here, this palladium Cl2 is in presence of this triethyl amine. So here first this elimination of one chloride and this nitrogen coordinated to the palladium, then the beta hydride elimination occur from this palladium 2 hydride, then this palladium hydride is reacting elimination of HCl to form this palladium 0 and the HCl. So by using the amine, so palladium 2 is converted to the palladium 0. So next, when use the palladium acetate, so that time using the phosphine ligand PPH3. So here first the phosphine is coordinated to this palladium metal. So then this nucleophilic attack of this acetate anion on the phosphine to form this intermediate. Next, the reactive elimination occurred to from this palladium 0 intermediate. So that's in this process, palladium acetate here, the palladium is oxidation stage 2 is reduced to palladium 0 to in presence of PPS3 ligand. So again, when some use the palladium chloride in the palladium 2 in the organoalkyl reagent, so then this from this palladium L2 R2, then the reactive elimination from of these 2R to form this palladium 0 and this alkene moiety. So here by using this organometallic reagents, N-butyl lithium or trialkyl aluminium, this palladium 2 is reduced to palladium 0. So here this is the many possibility how this palladium 2 is reduced by the reduced to the palladium 0 by various reagents such as amines, phosphine, or organo metallic reagents such as n-butyl lithium, trialkyl aluminium. So next I will discuss about the Heck reaction. So Heck elimination, or the simply the Heck reaction, was discovered independently by the efforts of the scientist Heck and Mizorki. The classical Heck reaction involved the palladium catalyzed substitution of the vinylic hydrogen with this vinyl, aryl, or benzyl group. So the coupling can be intra or intermolecular. So palladium as a palladium 2 in the form of salt or complex, or palladium 0 or concentration of 1 to 5 mole% is the most widely used catalyst for this reaction. A base is necessary to remove the liberated acid, with HX. This is the coupling reaction, is a stereoselective with the propensity of the trans coupling as a palladium halide group and the bulky organic residue move away from each other. Other in the reaction sequenced by the bond rotation. The typical catalysts are the palladium 0 phosphine complex, which is the PPS3 whole 4, or in situ catalyst has a palladium acetate whole 2 PPS3, and chelated phosphine are larger in bite angle such as the DPPF, or has also been used in several cases along with the palladium acetate, palladium 2 DB whole 3, or pi allyl palladium complex. So this is the example of the Heck reaction. So here in the Heck reaction, the vinylic hydrogen, this H is substituted by the other vinyl or aryl or the benzyl group. So this is the product in the Heck reaction, where palladium, mainly the palladium 0, palladium 2 or salt is used, which is in situ reduced to palladium 0 by other ligands. And here also a base is also used to remove the liberated HX from this coupling reaction. So here the stereoselectivity of this stereochemistry of the combination with the trans coupling, as the palladium halide group and the bulk organic residue move away from each other. So here this is an example of the intermolecular Heck reaction, and here also it is the example of the intramolecular Heck coupling. Here this bromide and this vinylic is coupled to form this CC bond. And here another example of the Heck reaction. Here the coupling with this isomerization. So first this bond is formed, then this double bond is isomerized to form this final product. So generally such reactions are conducted in the polar aprotic solvent like acetonitrile DMSO or dimethyl acetamide DM. The reaction time and temperature depend on the nature of the organic halide to be activated. Iodide derivative are the most reactive, and hence auxiliary ligand can be avoided. In the case polar solvents as a DMA and the NPP in the combination with the sodium acetate as a base are especially beneficial. So Heck reaction are useful on the inter and the intermolecular level. Although the intermolecular reaction are more common, the organic halide containing the beta hydrogen cannot be used, as they tend to form this olefin at the palladium 2 center, and electron rich disubstituted or cyclic olefin are less reactive than the electron deficient monosubstituted olefin. Many functional groups are compatible with this Heck reaction, which enables the synthesis of carbo heterocyclic compound at C-bonded isomerized product, including natural products. The active form of the catalyst is the 14 electron palladium 0 complex with 2 PPS3 ligand and 1 2 biglycerol insertion is often referred as the carbometallation in the palladium based catalytic cycle. So in the Heck reaction, the intermolecular both are possible, but the intermolecular Heck reaction is the most common. So here mainly the aryl halide iodide is used, which is most reactive, and for this Heck reaction the organic halide which has a beta hydrogen cannot be used, because in the upon beta hydrogen elimination, this aryl halide can form this alkene which is pointed to the metal center, which can deactivate it to the catalyst. And also the electron rich or disubstituted olefin are less reactive compared to the electron deficient and the monosubstituted olefin. So this is the catalytic cycle for this, for the Hague reaction. So here this is the active intermediate active catalyst for the Hague reaction. It is the palladium 0. So first this aryl halide, which is oxidative addition to this palladium 0 center to form this palladium 2 intermediate. Next, this alkene is coordinated to the metal center to from this metal alkene intermediate. Next, upon the insertion reaction occurred, which is called the carbometallation between the aryl ring and this vinylic hydrogen. So from this intermediate, then beta hydride elimination occurred. So from this alkene intermediate, which is upon elimination, to from this palladium hydride, and next this base in presence of base HBr is eliminated and palladium 0 active catalyst is regenerated. So this is the catalytic cycle for the Hague coupling reaction, where the palladium 0 intermediate is the active catalyst, and here the oxidative addition reaction is occurred. Then the insertion of this aryl ring into this alkene to form this intermediate. Next, beta hydrogen elimination to form this alkene. Next, dissociation of this final product to form this metal hydride species. So discrimination in the reactivity is possible in the Hague reaction by confirming the reaction condition. In following reaction, when PPS3 is not added, only iodide is replaced by the acrylate, where upon addition of this bromide also react, giving the trialkyline substitute toluene. So here, that means we can control the reactivity of this in Hague reaction. So here, when this PPS3 ligand is not added, that time only this aryl iodide bond is activated to form this final product, and when the PPS3 is added, that time the aryl bromide ring also bond is also activated to form this final product. So here, upon addition of the PPS3, both aryl bromide and aryl iodide bond is activated, but in absence of PPS3, aryl bromide bond is not activated. So that's why we can control the reactivity in the Hague reaction. So next, I will discuss about the Suzuki-Miura coupling reaction. So Suzuki coupling reaction can be described as a parallel catalyst. First coupling reaction of the organo-boron compounds, usually the boronic acid or ester, or with organic halide. So with the organic halides, so this is the classical example of the Suzuki Miura coupling reaction. So here this organic halide is coupled with this organo-boron compound to form this carbon-carbon bond. So here organo-boron compounds mainly use the boronic acid or ester. So here where BiO2 organoboron may be the BOH2 or the BOR2 or the 9BBA or like this, or X for this RX, X can be iodide, bromide, or OaSO2, or also the chloride. And here for this R group, maybe the aryl, alkynyl, also the alkyl, and the R dash may be alkyl, alkynyl, and the palladium is the PPSC whole 4 or palladium Cl2 or palladium acetate, palladium DB whole 3, and the base is used like the sodium carbonate or sodium ethoxide or TiOH or K3PA4 or CSF. So this is the one of the most powerful reaction in the synthetic organic chemistry for the carbon-carbon bond formation, and as it can tolerate the presence of the functional group in the coupling partner. Older conventional method for the coupling of aryl groups typically require reagent and catalyst are not the incompatible with this molecule bearing polar functional group. The Suzuki coupling reaction requires condition milder than the Heck reaction. So the boronic acid are air and water stable as well as the non-toxic. The pharmaceutical industries therefore prefer these reactions in the boron species that is formed as hydrous is relatively non-toxic. Recent development in the catalyst and methodology has enormously broadened the possible application of this reaction, and the reaction partners are not restricted to the aryl only, but include alkyls, alkenyls, or alkenyls, trifluoroborates, organoboranes, or cyclic borate. Ester also can be used in the place of boronic acid. However, the use of the necessary component of the reaction, one difference between the Suzuki reaction and the stereo coupling is that the boronic acid must be activated with the base. The activation of the boronic atom ensures the polarization of the organic ligand and thus facilitate the transmetallic reaction. So here, this is the general catalytic cycle for this Suzuki Mayura coupling reaction. So here, the active intermediate, active catalyst is the palladium 0. So first, the aryl halide is oxidative addition to this palladium from this palladium 2 intermediate. Next, in presence of base, this halide anion is removed from this intermediates. Next, the transmetallation occurred between this intermediate and this organoborane from this palladium 2 intermediate. Next, the reactive elimination of air dash and air from this palladium final product and palladium 0 intermediate active species is regenerated. So here the first this is the one of the important step the transmetallation where the the exchange of this air dash and the OR with this organoborane and this palladium intermediate to from this to get our desired product. So this is the example of the some synthesis of this bioactive compound using the Suzuki Mayura reaction. So here this organic aryl halide coupled with this boronic acid to form this compound which is called the retinol, and this polyphenylene paraphenylene also synthesized by using this aryl halide and this boron esters. So there has been a improvement and increase the scope and the utility of this reaction in the recent past. This includes the use of aryl chloride as a substrate to ability to conduct the reaction at very low catalyst loading, to carry out the reaction at the room temperature, to couple highly hindered substrate, and to carry out the asymmetric synthesis. So the phosphine component in the metal catalyst has also undergo wide changes. So an important breakthrough came in 1998 from the work of Stephen Buchwald and Jarjari from MIT. They found the system that could catalyze coupling of the aryl chloride under mild condition. The Buchwald system used a palladium with the electron-rich phosphines bearing biphenyl, while the FU system contains the bulky aromatic phosphine. They are able to achieve the Suzuki coupling of the aryl chloride even at room temperature. Buchwald later came up with the further modified phosphine, which performs even better. So this is some example the phosphine ligand used in this Suzuki coupling reaction for this activation of this aryl chloride. So first in 1999, so this Buchwald introduced this phosphine 1 complex. Next, In 1999, again the Bhopal introduced this phosphine line complex, and this phosphine S-phos is introduced by Bhopal in 2004 to activate the aryl chloride for this organ Suzuki-Myra coupling reaction. So success of these ligands are over conventional phosphine has been due to the combination of two factors. So this electron richness enhances the rate of the oxidative addition of the aryl chloride to the palladium, and that prevent the palladium complex from the precipitating out, and the steric bar enhances the rate of the reacting elimination. So in the addition of this, in the presence of this ortho-biphenyl moiety, confirm the air stability of the ligand. So these three phosphine ligand enhance the rate of the Suzuki-Myra coupling reaction due to the mainly the two factors. One factor is the this phosphine ligand has a more electron rich, so which facilitate the oxidative addition of the this aryl chloride in the to the palladium. And second reason is that these phosphine ligand are also in the very much steric, so that helps in the reactive elimination step. So that's why these phosphine ligands are more reactive compared to the other. So this is the example of we use this phosphine ligand. So here this aryl chloride in presence of this organoborane to form this final couple product. So when the phosphine 1 is used, then that time 85% of the product is obtained. When phosphine 2 is used, that is 91% yield of the product also. So phosphine 2 is the more reactive compared to the phosphine 1. So again, this is one example when phosphine 3 ligand is used, that time the 98% yield of the corresponding couple product is obtained. So this is the other example. The use of this phosphine ligand to form this couple product. So the coupling of these alkyl groups bound to the 9 ppm to the aryl or vinyl moieties become the possible by the use of the bis diphenyl phosphonic kerosene. The large bite angle of DPPF is believed to produce the catalyst with a more favorable rate constant for facilitating ductile elimination or beta hydride elimination. So in 2001, who showed that even alkyl coupling was possible at room temperature, but using the electron rich and the bulky alkyl phosphine like PCY3, and this strategy used can also make the oxidative addition of the alkyl halide facile in the prevent the beta hydride elimination. So coupling between the alkyl moiety is more challenging. So due to the presence of other beta hydride hydrogen in the alkyl group, which can beta hydride eliminated from this alkene moiety, and also the oxidation addition to this alkyl halide is not that much facilitated. So using the more electron rich phosphine ligand that will facilitate the first step, the oxidation addition, and the more electron bulk phosphine ligand will facilitate the reactive elimination to stop the beta hydride elimination. So in 2004, the food group used the bulky DPPF phosphine ligand. So from this alkyl coupling reaction, they got 88% yield. In this case they use 9 ppm boron organoboron compound in presence of DPPF phosphine ligand. So this reaction condition have also undergo a variety of changes. This includes carrying the out of the reaction in the ionic liquids or in water with the microwave radiation, and conducting the reaction with extremely small amount of palladium. Nicholas Leadbetter was initially proposed that the reaction could be carried out even without palladium under microwave condition, Later found out it was the palladium impurities in the ppb quantity in the commercial in a distributor that brought about the Suzuki coupling under microwave condition. So this is the here this alkyl bromide react uses 9 ppm organoboron compound to form this final couple product. So in presence of microwave condition, also the Suzuki coupling reaction can be formed. So the following example show how the Suzuki reaction has been extended further to the coupling between the two unactivated primary or secondary alkyl and between the alkyl aryl groups. Nickel based catalysis along with the amine bases are often required for this reaction. So this is the example of other. So even the nickel CO2 COD whole 2 nickel chloride also can be used to coupling between this alkyl this aryl halide and this organoboron compound. So for a long time, aryl fluoride seemed inaccessible for the Suzuki coupling reaction. The first example of the Suzuki coupling reaction involved perfluorinated arenes was reported in 2006 by Udo Radius and his co-workers. There has been a great interest among these chemists in CF bond activation reaction in part of synthesis of fluorinated drug analogs. The very strong CF bond helps the modulate the lipophilicity of a drug to improve its bioavailability, help control the drug metabolism. So far, so the most coupling reaction have involved the converting the monofluorinated arenes into the non-fluorinated derivatives, while the fluorinated arene product have been remained elusive. So Radius group has developed a nickel catalyzed stabilized a heterocyclic carbon ligand that selectively activates the CM bond para to the electron withdrawing CFC group in the perfluorine or group in the perfluoropinyl. The catalyst then mediates the coupling in the intermediate with the phenyl or biphenyl boronic acid to form the polyfluorinated biphenyl triphenyl product. So this is the example of the Suzuki coupling reaction with this aryl fluorine moiety with this boronic as this organoboron compounds to form these coupled products. So here this CF3 para to the CF3 is activated in under the reaction condition to form this coupled product. So next I will discuss about the Sonogasera coupling. So Sonogasera coupling reaction is another coupling reaction which is coupling between this aryl halide with this alkynes to from this coupled product. So this coupling of the terminal alkynes with this aryl or vinyl halide is performed with the palladium catalyst as a CU1 as a co-catalyst and the amine base. So typically the reaction requires anhydride and an aerobic condition, but never proceed have been developed where these restrictions are not important. In the Sonogasera reaction, alkynyl cuprate formed in the reaction of the copper with this alkene reacts faster with this palladium catalyst. The reaction is very similar to Castro-Stevens coupling, where the cuprous acetylide is coupled with these aryl halides in presence of the base under drastic condition. The Sonogasera coupling usually uses mild condition, open room temperature, and therefore it can be tolerated in the presence of large number of functional groups. Sonogasera coupling is a trimethyl alkyl followed by the treatment with the strong base. Fluorinated source is commonly strategy for the introduce the terminal alkyl groups. So this is the example of this Sonogasera reaction where this aryl bromide reacts with this alkynes to form this coupled products in presence of the copper hydride and this amine base and the palladium catalyst. So if Sonogasera reaction is performed on the haloalkene The geometry about the double bond is usually preserved, making this is an extremely useful reaction for synthesis of the inine molecule with the specific geometry. The reaction provides a method for making even conjugated acetylenic compound, an important class of molecule that have been found in the application in diverse areas, ranging from the natural product and pharmaceutical molecular organic material. So when in case of the alkynyl, when haloalkene is used in case of in the Sonogashira reaction which coupled with the alkyne, so that case the stereochemistry of this alkene bond of preserved. So this is the one of the important aspect of this reaction. So this is used in this synthesis of various evaluated compounds. So this is the catalytic cycle for the Sonogashira coupling reaction. So here the palladium 0 is the active catalyst for this coupling reaction. So first this aryl halide is oxidative addition to form this palladium 2 intermediate. Next, in presence this alkene moiety in presence of the triethylamine with react with this copper halide to form this copper alkaline complex. So here this use of the base for this reaction is used for activated this alkene to abstract this alkene hydrogen to form this copper alkaline complex. So next they are react with this palladium 2 intermediate to form this palladium alkyne intermediates named they comes in the this aryl group and this alkyne groups come in the cis position. Then the reductive elimination occurs to form this coupled product and palladium 0 is regenerated. So this is the example where this first the oxygen addition occurred, then this copper alkyne complex is coordinated to the middle center and next the reductive elimination occurs. So the Sonogashira coupling has found is used in the synthesis of the jet indines, which are useful substrate in the Bergman cycloaromatization reaction named Professor Robert G. Bergman. Although he has not used the first report, their information from the jet indines, he was the first to propose the proof the existence of the one for aryl radical intermediate. The reaction was largely ignored till 1980 when the indine class of the anti-cancer drug was discovered. The cycloaromatization occurs when the jet indine is heated. On for diradical form leave the H radical in their ethnicity to form this aromatic ring. So diradical can even abstract the chloride atom to form the CCl4 to form this para dichlorobenzene. Dissolving the oxygen, it can form this quinones. So the Sonogashira has been also extended to unactivate the alkyl bromide using NH ligand such as. So here in thermal condition. So here this indines to form this cycloaromatization to form this 1,4 aryl radical with upon elimination of 2 hydrogen radical to form this benzene ring. So here Sonogashira reaction. This is another example. While this alkyl bromide to couple with this alkyne in presence of this NH ligand to form this coupled product. So Sonogashira reaction can also use to form this to activate it to this alkyl halide intermediate. So this is the for this Sonogashira reaction. So thank you.